there come from? So to motivate those two things, why we need a toy model and where will the toy model come from, I'm going to give you a few facts about de Sitter. Some of you who
maybe you could use bigger font size. Yeah. Okay.
Do you want me to write this bigger?
No, bigger than that.
But do you want me to erase it?
No, no, it's okay.
For the future, I will.
Yeah.
Okay. So for those of you who were at my lectures at the Engelbrecht Mandelstam School, this may be a bit of repetition, but as I've been told in the past, nobody gets mad about hearing things they already know. So let's go with that. So the idea is that we are interested in de Sitter space. So what is de Sitter space? Well, it is the simplest cosmology that one can study. So the geometry is one where, so here time goes up, and as time goes up, so if this is x0 equals 0, the spatial slices grow in size. And this is a maximally symmetric space. Okay, so let me write down an equation for de Sitter space. So one way to write it is as a constraint in one extra dimension. So it's a constraint on d+1 variables in d+1 dimension with one constraint. So this describes a d-dimensional spacetime, which I will call ds. Okay, and you can see that this this is a maximally symmetric spacetime just by analogy with the sphere. So if this didn't have a minus sign over here, you would see that this is an equation for a d-sphere. A d-sphere is a constant curvature geometry. Constant curvature, the curvature is given by this length scale, which I call L. And sphere being maximally symmetric, you can see it has, you select any two of these coordinates, and that defines a rotation plane. And the maximal symmetries of the sphere are just rotations around each one of those points. Similarly, for de Sitter, it's maximally symmetric. You just replace one set of rotations by boosts because this is a minus direction. So, so the symmetries a group and that group is known as SO, the special orthogonal group, 1, D. So SO 1, D is telling you that you have one Lorentzian direction and D -1 spatial directions. So if I had instead, so you should think of this in analogy with the sphere geometry. So sphere, the symmetries from the group SO D+1. D sphere from the group SO D+1. So you see that the fact that you just have one Lorentzian direction means that you should think of it as SO1, which is the Lorentz group in D+1 dimensions, right? Lorentz group in D+1 dimensions because this is a constraint in a D+1 dimensional Minkowski space. Okay, so this is the space-time, and we're interested in the space-time because, as I mentioned, it describes the simplest the simplest type of accelerating cosmology. And we know that our universe had two phases where this type of geometry is relevant. One is inflation. So inflation, you had an accelerated expansion of space from the very early universe, matches very nicely with experiment. For example, the C and B fluctuations, the flat slicing of the late universe that we observe now. And also, we have observed more recently that the universe is slowly approaching a late phase of de Sitter, and that has been measured by measuring type 1a supernova in the sky. And we see that the late phase of the universe is driven by something called dark energy, or a cosmological constant, which means that in the future, our universe will tend to a universe like this. So there's good reason to want to study these geometries. And now I'm going to tell you a couple of facts.
So Tarek, maybe let me ask you a question. So x naught equal to 0, that would be the Big Bang. I mean, if we model our universe, or is it like a cyclic universe type of situation?
Yeah, you can think. Okay, so for inflation, one way to think about it is that we start here. There's no Big Bang. There's just you nucleate a universe of some size. It's not zero size. Just nucleated using some process. We don't know what happened before that, and then you let the thing go.
Okay. Yeah.
So mapping solutions does not.
Thing that we thought of as the final stages of inflation. Is that what?
No, the final stages of inflation would be up here.
Nice.
Great. So you start from something where the spatial volume of the universe is very small, and then you inflate for something like 60 e-folds, and then you get something very large. That's 60 e-folds is a lower bound. It's not an upper bound. Could have inflated much longer. Right. So this geometry is very relevant. It's also very nice because it's maximally symmetric. So it's a very nice place to start studying quantum field theory outside the realm of Lorentz invariant quantum field, just regular Lorentz invariant quantum field theory. We can now put it on this background. And this background has a lot of symmetry, just as much symmetry as Minkowski space. However, it doesn't have the symmetries that we like to label particles with. So this geometry does not have translation symmetry. So you can see that here, time translation is not a symmetry. Everybody knows what the Noether charge of time translation symmetry is?
It's the Hamiltonian.
It's the energy, right? So that means that there's no energy conservation. And also because there's no translations, there's no energy or momentum conservation. Okay, and something that we take for granted when we think about QFT. So when we learn about QFT in flat space, we start with the harmonic oscillator, like free quantum field theory. And free quantum field theory, you build up this idea that you have these individual particle excitations, and you build on top of the vacuum those particle excitations. Each one of them comes with their characteristic energy, right? And then energy, you act with creation operators, energies add, right? And then as energies add, you start with some state of a certain amount of energy, and as you evolve in time, that energy stays conserved. In de Sitter, there's no good notion of energy. It's not the Noether charge associated with anything. So this harmonic oscillator picture kind of goes away. It's not a reasonable thing to assume that understanding of the simple harmonic oscillator is going to hold in de Sitter. So we basically need to come up with a simpler picture that applies in this geometry that is as simple as the simple harmonic oscillator and yet captures the physics of mystery. So that's the goal. That's the goal for finding this total. Okay.
Is there a problem with defining the vacuum state? There is a problem, right? Okay.
Right. So, okay. So, yeah, something that I didn't. Well, we can get into it if you want, but we don't have to. Is that there? Okay. So you can pick a vacuum for de Sitter, and one particularly symmetric choice is, if you look at the time-dependent physics, it will look thermally populated. That's just a statement that in Euclidean time, so if I analytically continue this to Euclidean time, this guy becomes like one of the angles, and it's periodic. It will be periodic. Anything periodic in Euclidean time is there.
Just I guess it kind of is static patch.
So you can conclude that de Sitter is thermal in all patches. The static patch is particularly nice because then there's a horizon and you can use the equivalence principle, like any Rindler observer. And so it describes Rindler observers. Any Rindler observer is going to notice a thermal fluctuation. But even if you work in the global patch, you just can see that the Euclidean time is periodic.
Maybe one more small question. How about angular momentum?
Angular momentum is conserved.
It is conserved, right?
It is conserved.
Yeah.
But one thing that you learn, very important distinction between energy and angular momentum, is that angular momentum can be negative. You can have angular momentum pointing in the opposite direction. Energy is always positive. Right? Have a ground state and we add energy on top. Here, we say that the spectrum for angular momentum is two-sided. Lower the angular momentum as much as you want, you can raise it as much as you want. We don't like it when you can lower the energy as much as you want, because when you say that you can, then you conclude that this system is unstable. Okay. So let's work in a very simple example. I'm gonna move away from general D dimensions, and I'm gonna move to DS2. DS2 is particularly simple. So the symmetry group is SO1, 2. And this is actually equivalent to the group SO. Special linear group in 2 dimensions. Okay. Have you guys seen this group before, SL2R? So also known as the conformal group of 1 dimensions. So if you have SL2R invariant theory, then you know that it is also a conformally invariant theory. At least conformally invariant quantum mechanics will have this symmetry. So de Sitter in 2 dimensions has the same symmetries as a conformally invariant quantum mechanics. Okay. So now let me tell you a little bit about the allowed representations of this symmetry group, SL2R. So SL2R has is my handwriting big enough for the?
Yes, it is.
Okay, so the simplest representation of SL2R is something known as the discrete series. Actually, before I get into this, let me give a little bit. few equations on SL2. Here. Okay, so SL2R is the theory, is the symmetry group that is generated by three generators. One is this thing called L0, one is L plus, and one is L minus. So if you've ever studied CFT, two-dimensional CFT, you will have seen this. The algebra of these operators is L plus minus with L0 is equal to plus minus L plus minus and L plus L minus equals L0. So if you want to think about it like a harmonic oscillator, L0 measures the energy. L plus the energy unit. L minus lowers the energy by 1 unit. SL2R, just as any theory that admits these three operators. Any theory with these operators no matter how you choose to write them down in terms of basic quantum fields, in terms of X and P and quantum mechanics, any theory that has these operators that act unitarily on Hilbert space is a theory with an SL2R symmetry. Okay, and this just so happens to also be the symmetry group of two-dimensional distinctions. Okay, so what are the representations of no, I think you can. I'm just giving you if we're going to start by thinking about the symmetries first. So yes, I want a unitary quantum field theory.
So if I have a
Free scalar for
is it good?
It's good.
If you put a mass on that, still good?
Yes.
Great.
But I'll give more details slowly. The point is that there have been many incorrect statements made in the literature because people do not first think about what the allowed representations are of the de Sitter group, and then because they don't know how these representations behave, then they'll say things, de Sitter is unstable, there's bad things. Okay. I'll add details. Okay, so the discrete series is exactly what you learn in conformal field. Okay, so the discrete series is sometimes called the highest weight representation or the lowest. So what this means is that there is some state. I'm going to call it delta. And if I try to act with L plus on it, I get 0. Think about that like the harmonic oscillator. There's a ground state. If I try to act with a lowering operator on the ground state, I get 0. And then the whole Hilbert space is generated by L minus. Right? And these have L0 eigenvalue that is the lowest eigenvalue plus n. Or minus. So we work in the highest weight representation. L minus lowers, the energy is minus the L0.
So why delta is still there in the?
Because delta labels the whole representation. So for example, think about, so when you learn about angular momentum, you have two eigenvalues. You have L and M. L labels a whole representation, and there are various M's that you're allowed in that representation. So delta is like L, and N is like N.
Okay.
So delta labels the whole representation, N tells you what state you're in that representation.
So then why are you calling delta the vacuum state? I mean, it should be.
No, it's a label for the representation. One way to label a representation is that there's this thing called the quadratic Casimir, which we call C2. C2, in terms of these guys, is L0 squared minus 1/2 L plus L minus minus L minus L plus. And if I act with C2 on any delta comma M, I get delta times delta minus. Doesn't matter which n. Just like if I act with the Laplacian on the sphere on any YLM, I'll get L times L plus 1, independent of what n's. Okay, so that's the discrete series. That is the most conventional type of representation. You guys should be very familiar with it. It behaves exactly like a harmonic oscillator. This is the basis of every textbook on conformal field theory, highest and lowest weight representations. However, if I try to represent this series as a scalar field in the center, so I try to get this as a free QFT on DS2, then I need something like my action to be square root minus g, phi squared, minus plus m squared, phi squared, and m squared has to be tachyonic. That already signals something bad.
Sorry, one question. So the discreteness is coming from the discreteness in N, is that correct?
Correct.
And series, where is the series here?
Series is just how mathematicians call representations. You'll see that this name appears all the time. It's not a very useful name. It's just what they call it. So now if you ever see it in the literature, you know what it means.
What is it, vacuum?
That just has to do with, so in de Sitter, C2 is, so for this scalar field theory, C2 would be minus box. And the Casimir eigenvalue, so the equation of motion is minus, so, right, C2 phi is equal to minus phi. And you can think about this as the eigenvalue equation for the quadratic Casimir, and for you to match this discrete series. Discrete has to do with the fact that delta is in 1, 2, 3. These are the admissible deltas.
Yeah. So it has to be vacuum for consistency.
Yeah, in order for this to be the equation for this series, m squared has to be a type.
If it is a representation.
If it is in this representation. So the representation that we think we like the best as a free QFT on de Sitter is the weirdest. It's a type. So this should suggest that maybe we shouldn't think about these at all. But actually you can't avoid them. I'll tell you why in a second. So the next I can't write it over there. So So the next representation that I want to talk about is something called the continuous principal series. So the continuous principal series, unlike the discrete series, no state is annihilated by L plus. No state ever gets annihilated by L plus. So delta in the discrete series was 1, 2, 3, 4, 5, so on. Those would be allowed values. Here, delta has to equal 1/2 plus I times the real number. So delta is complex. Okay?
That should be half.
The real part has to be half. That's required by unitarity.
I think that.
Huh? Unitarity. For these operators to act unitarily on Hilbert space, this eigenvalue has to be 1/2 plus I.
Sounds like Riemann.
Many people, in fact, Fadeev was interested in. So, among other things, where SL2R appears, the Laplacian on the hyperbolic disk, and in 2 dimensions, and Fadeev knew that some eigenfunctions on the hyperbolic disk had these eigenvalues, 1/2 plus I real, just comes from symmetry. And he believed that maybe he could understand the Riemann hypothesis by studying those eigenvalues.
This is for all reals, right? What Riemann, the zeros are some discrete numbers.
Correct.
You know,
He wanted to find some special solutions. I have nothing to do with the Riemann hypothesis. In fact, I would like to avoid talking about it because I think that if this is getting recorded, then it might appear to be a crackpot if I talk about it. Okay, so the way that this representation works is so if I have L0 on delta comma n, then this is equal to n, and L plus minus just raise this n to plus or minus with some coefficient. Okay.
Is this representation in any way related to the continuous representatives of the Poincare group?
It's exactly the same. Yeah, it's exactly the same. So it's the higher dimension. So in Poincare, you have the part that is the translations, which are labeled by energy and momenta. But you could also work with the Lorentz generators, which is exactly what I'm working with here, and then you would get these exact. It's not the continuous spin representations.
Yes, I get that.
No, it's not those. No, it's a different part. These are the representations that if you've seen in the celestial holography literature, these are the ones that they're focusing on because they're trying to write everything in terms of the Lorentz generators that act on the sphere at infinity rather than the translations. But it's not the continuous spinings. In principle, you can take any flat space QFT and relabel every state in terms of these labels, if you want. It's like working in the Mellon basis. But you see, here there's no notion of a ground state. You can raise the L0 eigenvalue as much as you want. You can lower it as much as you want. It acts like an angular momentum. And this one is represented by an equation like this, where n squared, L squared is greater than 1/4. So it happens to be the case. So this is very accurately represented by a free quantum field theory with a mass above some, low. Okay. And then there's one last one, which is called the continuous complementary series. And this one has delta between 0 and 1. But for all other purposes, it behaves exactly like this representation. There's no ground state, there's no state that's annihilated by L plus or L minus, and L plus minus just raises this. And that's represented by a light scalar in this m squared L squared less than in DS2. Okay, now why did I say that you can't get rid of the discrete series even if you wanted to? Well, that's because, say I take two wave functions from the principal series. You know, we learn about this very annoying thing when we learn quantum mechanics, is that if you have two wave functions and each one has angular momentum and you want to ask what the angular momentum of the total system is, and there's some decomposition called the Clebsch-Gordon decomposition. Right? It's very annoying to like rewrite this product of wave functions as sums over single wave functions of the center of mass. Okay, so you can ask what happens if I take two principal series reps, PR, potentially PR. That's the mathematical thing we do when we multiply two wave functions together. And we ask how this decomposes. And it turns out that mathematicians show that this decomposes into a sum over a discrete equal by n plus an integral. So even if you want to ignore the discrete series, if you just have single particle states in the principal series, when you bring them together, the bound state will be a bunch of heavy particles plus some tachyons. It's very strange. It's very strange. And this is exactly what goes wrong with the harmonic oscillator picture. You add two together and you get more energy. Here you add two energies together, you get more energy minus some tachyon. And there's no good understanding of this fact from local QFT. I just don't understand it. Nobody has written down a QFT model that has this feature. Okay, so we don't understand it, and I would like to understand this better. Okay.
So we are still in de Sitter, right?
All of this is just representation
So
theory of SL2R.
Isn't this a reflection of the fact that energy is not conserved?
Right, right. But so I don't know how to represent these states, these discrete series states, using this simple kind of. So when we have bound states in QFT, what we do is we say, oh, we have some EFT. The bound state can be represented by some meson Lagrangian. We know the meson is not fundamental. The meson Lagrangian looks like any other Lagrangian, right? It just has a kinetic term, some mass terms. There's no nicely behaved free Lagrangian that describes these bound states. I don't know how to describe it.
So, I mean, if one was just talking about normal conformal 2D conformal physics, you wouldn't worry about these representations because this speed series doesn't give you tachyons and it's just all.
Correct. Exactly. It's because the sign of m squared L squared, you go the opposite direction. So,
and this is specifically a property of the Casimir in this.
Correct. So in just regular conformal field theory. So okay, you might ask, why don't I see these states in conformal field theory? The regular kind that you learn. That's because okay. So one nice thing is that if I show multiply two discrete series together, I would get discrete series. So that's this energies adding. And okay, so completely true what I said. Symmetry is given by now. I also have to tell you how to Hermitian each generator. So what is the Hermitian kit? So when we learn conformal field theory, we work with a norm that is natural from the point of view of the Euclidean cylinder. And that norm is not compatible with the sphere, the Euclidean sphere, which is important for this. So there's a different choice of norm. And with that choice of norm, it's much more natural to ignore the principal series states. Actually, with that choice of norm, the principal series are not unitary, and you only have discrete series. The other choice of norm, you have them all, but it's very natural to think about the principal series. So, okay. I think I'm not doing very well on time, but
It's okay.
okay. So, all right. So we're in this. So all of this I've just told you. I haven't really talked about de Sitter very much. I've just talked about symmetries, symmetry algebra, how they act, what you should expect if you study the symmetry group of two-dimensional de Sitter. Now I'm going to tell you a very simple toy model that has this SL2R symmetry. And it's okay. So if you want to learn about SL2R, one of the nice examples is something called the Di Alfaro-Fubini four-line model. Have you guys heard of this? Have you ever heard of this? No? It's called DFF model. And it is the simplest SL2R invariant quantum mechanics that I've ever seen. And nevertheless, it's very illuminating to study. So it's just one degree of freedom. And we write it like this, the Hamiltonian R squared, I'm gonna write it like this, delta So it has a Hamiltonian. So it has a Hamiltonian that has 1 over R squared repulsive potential. 1 over R squared repulsive potential. It has a K. So this is usually called the generator of special conformal transformations. But here it's just R squared over 2. And it has something called the D, which stands for dilatation operators. And this, so R dr plus 1. And this R coordinate goes from 0 to infinity. So it's a radial type coordinate. Okay? And I can form this algebra by taking L0 is equal to H plus K over 2. And L plus minus is H minus K minus plus. Okay. Now L0, you see, it's like this repulsive potential that I add to it a harmonic trap. Right? So the potential then looks like this. It's a repulsive Coulomb. No, Coulomb is 1 over R potential. This is R squared. So in fact, I'll get to it. I'll get to it in a second. Okay, so if I write V of R versus R, No, V of R for L0. I've added H and K, so V of R for L0. Yeah, so H the L0 is H plus K.
L0 I understand. Yeah, that's English, right? But what is VR?
So it's VR. So if I just imagine I take this and I add to it R squared, and I don't ignore the connection.
Okay.
So now you see that the L0 eigenvalue, there will be a bunch of balanced state waveforms. And that's exactly what you would expect, right? So L minus or L plus raises the energy, and it acts just like a harmonic oscillator. Okay? And this is a conformally invariant quantum mechanics. Has all of the nice generators of and the whole represent, and if I compute the C2, so I put this delta in here. So the C2 is delta times delta.
But if you just look at the arguments,
They're playing. They're This is just the simplest SL2R invariant quantum mechanics, and this describes the discrete series. Okay, and the whole Hilbert space is just one representation labeled by delta, and the L0 values are 0, 1, 2, 3, 4 that you get. There's a state. This state right here is annihilated by L plus. And if I act with L minus, I raise it. Okay.
Is there any way of thinking this geometrically, or it's just some special quantum mechanics with a special potential which gives you?
So do you want? You mean like a real world system that has this? Yes. Actually, you can think it's a very nice set of papers. Actually, I think this quantum mechanics. It was realized by Jakiv that this is the quantum mechanics that you get when you just think about the radial behavior of a electrically charged particle in the background of a diamond. So it has both magnetic and electric charge. And he noticed that it had all of these wave functions and dilatations. It's like beautiful SL2R symmetry.
The expectation value of number in these states is positive.
It's positive, but they're all scattering states, so there's a continuous.
Okay, just slightly. So then the SL2R symmetry that summarily to down.
Yeah, totally. Yeah, exactly. Yeah, in fact, you can even supersymmetrize this quantum mechanics. All the wave functions were done by Vinet and some other authors, Doker. Okay, but so this quantum mechanics is exactly the type that I don't want to consider, because this is the one that's good for like regular, conformal field. So people studied these when they wanted to learn about conformal field theory. And actually, this quantum mechanics has a very nice generalization to n particles. So the n particle generalization is called the Calogero.
but I can ask you, why do you want to constitute this quantum mechanics?
I'll tell you in a second.
Okay.
Just we'll get there. Is that how bad am I doing?
You have time.
I have time. Okay. So I'll explain. Just give me like 5 minutes. So the Calogero model is this quantum mechanics, but now you think of n particles. And the Hamiltonian is the following.
So Tarek, time is 2:13.
Yeah.
You have to leave at what time? 3:30 or so?
You guys want to stay here for that?
No. You maybe accelerate a little bit.
I will. I have to give the introduction. So instead of having one particle with one of our square potential, you think of n particles, and you let them have an inverse square repulsive potential between them. Okay, they're all on a line, and there's an inverse square repulsive potential between them, and then k is the sum over ki, each individual particle, and d is the sum. And this quantum mechanics is very interesting. It's also SL2R invariant. It's also completely integrable. You can solve this quantum mechanics exactly for any n at any value of the coupling. And the wave functions are all of this type. They're all of the discrete series type. Okay. And okay, because it's integrable, there are a bunch of other extra conserved quantities in this quantum mechanics. It just turns out, it's kind of a beautiful thing, that all of those conserved quantities, if you take n to infinity, map on to all of the Virasoro charges. So this model has Virasoro symmetry, but at finite n, it's not the full Virasoro. It's just some truncated Virasoro. It becomes a full Virasoro as you take n to infinity. So this is really a nice truncated model of a CFT. Very simple CFT. You can solve this exactly. Learn a lot about CFT representation theory just by solving this. And so we review it in our paper. If you want to learn how to solve this model, it's not very difficult. Okay, so what does this have to do with this? Now, so far, I've just told you about this SL2R invariant quantum mechanics. I told you about how one way to think about the representation theory of conformal field theory is by thinking about the wave functions of some SL2R invariant quantum mechanics. Here is the n particle generalization. N particles is nice because what we know a QFT is just the n to infinity limit of an n particle quantum mechanics. So hopefully we can deform this model somehow and get some de Sitter physics. What's the simplest way to deform this model to get some get de Sitter physics? So remember, so these discrete series, so the deltas were constrained to take positive integers. So to get de Sitter, remember one thing we wanted to do was take delta is equal to 1/2 plus I real. Okay? So when I plug that into this equation, instead of having a repulsive potential at small r, I have an attractive.
So you're using the Hamiltonian complex then?
No.
I mean,
No, you can plug this into the Hamiltonian,
yeah.
and you'll see that you get a real number. Here, r can't go less than 0. So this becomes attractive. And actually, there was a very famous observation by, I guess, Landau. I don't know, you can find it in Landau and Lifshitz. To try to solve the quantum mechanics of an attractive 1/r, there's a problem. It's called the falling into the whole problem. I don't remember what exactly it's called, but it's in some chapter of Landau and Lifshitz. Is that there's no the density of states is very highly degenerate in this here, and there's no way to cut off this quantum mechanics in a reasonable way to get any like even plane wave normalizable wave functions. Just this quantum mechanics of an attractive 1/r squared is just there are just no good solutions to it, and people would say that this actually you might think that these form a unitary representation of SL2R, but actually they don't. I just analytically continue delta to have these values. It's attractive 1/r. So I can't represent this quantum mechanics as this particle in an attractive 1/r squared potential because I don't get a unitary representation if I try to solve for the wave functions of that quantum mechanics. Okay, so Nevertheless, we know that these are unitary representations. So what do we need to do to these operators in order to get a unitary irreducible representation? And I'll tell you what that is now. So actually, the observation was made in some papers maybe from 15 years ago, where it's that actually the problem comes from the fact that we restricted to R between 0 and infinity. In order to get a nice representation for this quantum mechanics, I shouldn't think about it like quantum mechanics for a particle on the half line with an attractive 1 over r squared potential. Actually, I have to do two things. So one thing is I'm going to relabel r squared goes to something I call kappa. Okay, so then this becomes 1 over kappa. And kappa now is between infinity and max. So I allow it to be on the full real number. So then k becomes 2. That means kappa. This is kappa. And there's another thing I need to do is the kinetic term actually becomes something like this. Kappa d kappa squared. No, no cutoff anymore. I'm defining a new quantum mechanics. So these, they actually also obey the SL2R algebra. But now you have to notice something.
You haven't changed the symmetry, just the representation.
Yeah, I've just changed the operators. Symmetry is the same. But now, here's something weird that happens if you want to think about this like a normal quantum mechanics. So one thing we always do in quantum mechanics is we take our momentum operator to be dx minus dx squared. And that's a positive operator, always. Right? E to the ipx, because p squared is positive. Here, there's a coefficient kappa, and kappa is allowed to be negative. So this is like a momentum operator or a p squared operator, but you're allowed to have p squared is negative. And if you solve for the wave functions of this model, you can get normalizable good wave functions that fill out this thing called the principal series. Okay. Sorry. It's actually
particle and whole.
It's very strange. Let me draw the L0 potential. So the L0 potential looks like this. And this is just quantum mechanics. So for kappa, it's linear in kappa, and then it goes like 1 over kappa on this side. On this side, the sign flips. So you would say it looks like this, and then it's the negative linear. But then also the moment the kinetic operator changes sign. So these are like they're actually normalizable. So this decays in this direction, it decays in this direction, so on. And then here it's but you see already you get a sense that energies don't add, right? Like in the way that you would normally expect.
And the effect of the potential is you flip the.
So because the kinetic term flips on this side also, then it looks like it's on its head again. It's very strange.
But is it doing some kind of analytic continuation or something?
Yeah, this is like doing the proper analytic continuation of the operators so that you get unitary representation of this algebra on the principal series. Principal series is what I say acts like a heavy particle in the system. Okay. So I guess this is illuminating. We can see that there's a little bit of weirdness, but we can learn something. That you can study this model to think. It gives you the simple toy model, the one representation to consider. But QFT has a bunch of representations, so we need to figure out how to like put representations together, make them interact. So we want to do the same thing to this model.
And for this, you have a ground, you don't have a ground.
No, so exactly. So there's no notion of a ground state. There's just it's just a whole state. It goes up and down, all the way up to infinity and down to minus infinity. So it really does behave like a massive scalar field. So there's no interaction, just a single representation.
Yeah, just take the variable like r squared to k or something.
Yeah.
That should not change in the Churchill terms, right? Or it does.
No, so then you have to solve for the normalizable wave functions of this problem. You have to resolve the problem.
You are taking the definition of time rules.
Yeah.
Okay.
Yeah. Just changing the whole all the definition of the operators. It's the analytic continuation of the operators. So that I get a unitary representation of SL2R, but that acts on the principal series. We want to act on the principal series. And so in order to do that, starting from that simple quantum mechanics of a 1 over r squared potential, I have to do these funky things. I can't just change the value of delta.
You're changing r squared to k, but you're not changing time. So
Well,
so it's
I have to change the domain of these operators. So before the domain was the half line, now it has to be the full. I can't define these operators on the half.
you're basically solving a different problem.
It's a different problem. It has the same algebra, and but it's a different problem. It's
Yeah,
different.
so in the previous language, we were solving our problem with keeping it on, then you make the time not dependent or something. In the previous language, right? Yeah. It's whatever that gives to us.
I'm not exactly sure I understand the.
No, it's just slightly complication about it. The fact that k into native values is just already taking imaginary values.
Right. So suppose you start with r Hamiltonian. So hr is equal to I into psi. That's what you're solving. Hr psi is equal to I h psi.
Before I was solving h psi of r equals e. Well, say L0 psi of r is equal to e n psi.
Now you're solving a little bit of different LCO. That generally means that you have made the time with you change the one variable in the left hand side, didn't make the change in the right hand side. It's kind of same as making the time space dependent in the previous problem.
If you want to think of them as analytic continuations of each other, but I don't want to think about it. I just want to think about this as a completely separate model that captures the
separate model that has the same.
it has the same symmetries, but it generates the principal series representation rather than the other representation.
Okay, just one. So I think earlier when you were describing the representations, I thought it's the discrete series that's problematic. And those had technical.
So indeed, but you see, you might the thing was, if you just think about principal series, you might think that you can build your entire QFT in terms of principal series. But what I'm saying is that if you try to start with a QFT with only principal series and then you take the principal series, you'll get the discrete coming out.
Okay.
So I'm going to try to do that with this model now. I have a bunch of principal series in it, and then see what I get. And okay, so I think I'm running out of time, but let me just say that you can do that to this model. So you can do a very similar set of manipulations. You go to the radial variables for this guy. You analytically continue, let the radial variable go to minus infinity. You also get a bunch of principal series reps that solve this quantum mechanics. However, one thing that you don't get is that it's no longer exactly solvable. So in the discrete series case, writing them like this, it's exactly solvable. You can solve the model exactly. Here, it's no longer exactly solvable. So So now we have an n particle quantum mechanics. The generators act unitarily on Hilbert space. We don't know how to solve it. Except we solved it for n equals to 2 and 3. We can do that. But n equals anything greater than 3, we don't know what to do. And it would be very interesting to see if we can understand this quantum mechanics better so that we can maybe one day learn how to extract lessons for QFT.
And so you're guessing that this is the dual of
no, not a dual. That's a toy model for just a QFT on top of this. Simple QFT on top of this with a bunch of states. Just like this is a simple toy model for a chiral boson CFT.
Okay, so let's thank Tarek for a very nice talk. Okay, more questions? We already asked. Yeah, yes.
No, it's okay. So these are really defined CFTs or at least one.
Yeah.
Can you make a CFT out of it or?
CFT, so this guy is a CFT at n equals to infinity.
Okay.
N is the number of particles.
Yeah.
So if I take n to infinity, then I get a CFT.
What about that?
Actually, it doesn't become a full CFT because there's an anomaly. Because this is, you can compute the partition function for this model for any n and lambda. You get the partition function of the chiral boson. We know the chiral boson is not quite a CFT.
It's half the CFT.
It's half the CFT. The central charge is not the right number to get anomaly cancellation. But it, you learned something. That's the chiral boson.
Okay. Yeah.
So you mentioned the issue about what the vacuum state of facility is. Is there? I mean, at this early stage, is it one of those shit light? Doesn't look like it just.
Not really. There's just a whole set of states. None of them is the vacuum.
Yeah.
I really would like to understand if we can bypass somehow solving this for every n and just take the n to infinity limit and get something. Maybe there's something there.
Yes.
Yeah, like a diamond, yes.
So for large in case that this will be some kind of CFT.
QFT, just the QFT on the symmetry. Because the symmetries are there.
That's the symmetries of a CFT, but it's not a CFT.
Yeah, if you put a QFT on AES, it has the symmetries of a CFT, but it's also not a CFT.
There's some symmetries with respect to the lambda, meaning so if you just study the collision model for lambda equals to 0 is bosonic and lambda equals to 1 it's fermionic. What happens to these kind of things when you analytically do it?
Very good. So the answer is going to be a bit technical. It's not. So how do we know that it's bosonic or anionic? Is the statistics of the wave function as you swap xi and xj?
Yeah.
Okay, so in order to get the de Sitter version of this model, one thing we have to do is we have to go into the center of mass and radial variables, and then actually it turns out that we have to throw out the center of mass to do it. Then we analytically continue the radial variable just like we did here, and then you lose this idea of particle swaps. And putting that back in, I don't know how without the center of mass. Like which one is the individual particle? Not exactly sure how to answer that question.
So this is more like a vector model, right? Like this is a matrix model question. No,
but it'd be interesting to find. Actually, this model you can derive as the eigenvalue dynamics of some Yang-Mills matrix model. So I don't know, it'd be interesting to find another matrix model that gives the analytic continuation.
Okay, looks like there are no more questions. So let's thank Tarek again. He's leaving today at 3:30, but he's available via email for
any
Discussions, future collaborations. Okay. Oh, hold on, let me check whether somebody is on Zoom. I don't see any questions in the chat. Okay, we are good.